right, we are now recording. Let's get set up. I think I discovered last time the old CD or DVD doesn't have this section in it from the previous thing, so I'm just going on here. This is just strategies for integration. This graph is from 7.7, not 7.6, because they don't have 7.6. But we started this last time about looking at, the strategies you would use to go about integrating. Let me get this covered first while I'm thinking about it. They did cancel class on Monday, which now makes us having an 8.5-week term rather than a 10-week term, because we lost Monday of Memorial Day. I think we had a Wednesday weather day, didn't we? It seems like we did. And let me see. No, I know what it was. We had a Memorial Day was a Monday, and then I had to be out. It wasn't a weather day. I had to be out a day because of a meeting that they should have scheduled for the weekend, and they scheduled it for New Orleans during the week, and that hacked me off. And then we lost this one, so we've now lost 3 classes out of 20, so not good. So we may not get as far as we should. I can try to, there's that. And then I think, as I told you last time we were recording this, I wanted to get this since very few people were here. I'm on the biology screening search committee, and I finished, let me go back. I finally finished all the screenings I needed to do. They had scheduled for last Monday a week ago. I couldn't do it because I was in class all day, so I tried to do it Tuesday, and they couldn't get the system to work because they've doing it all online now. When they finally got that up, I only had time to screen like 3 people, and 2 of the 3 were from what the other committee members had done on Monday. Looked like they had done them wrong, so that didn't look like a promising situation at all. So I had to take the forms home with me, and then I used all the office hours I had on Thursday to do the screening, and then turned around and had to take them home and finish them over the weekend. Bottom line is, I was behind in grading because of all that screening. Well, I got all the grading caught up over the weekend too, but I didn't have a chance to put it on Blackboard. So if you notice your grade's not on Blackboard, it's not that I don't have it graded, it's just I haven't gotten it done. I have 0 times a day to do that. Hopefully tomorrow, in some of the office hours I have tomorrow, I'll be able to get that done. Okay. Now, back to the biology screening committee. Sometime or another, they're going to schedule interviews. And I begged them, every one of them, please don't schedule on Monday or Wednesday because I don't have any time to do it on Monday or Wednesday. And I've got 4 classes to make up if I do. The odds are they're going to schedule on Monday or Wednesday, and then we'll lose another day. Hopefully not, but. And then when we're doing the screening, like I said, I found at least 2, I think 3, that they screened that they should be interviewed, and I screened said, no, they don't meet the minimum requirements. Well, they put one of those back in saying that, I can't believe this, is for teaching biology at, post-secondary level, okay? We had in our job description, must have taught biology at least 3 years on the post-secondary level or secondary level. Well, they screened a woman who had 1 year in high school and 2 years 7th and 8th grade science. I said, that's not high school. And the chair said, oh, but I found the example of where they say 8th grade can be. I said, well, this is 7th or 8th grade. Well, we're going to let her come in. In other words, we're going to interview a person that I think is automatically not qualified. But there's another interview today. So I don't know what we're going to do. Hopefully they'll get them all done on one Tuesday or one Thursday, and that way it'll minimize the time I have that I can't do. But that's beside the point. Okay, it could come up. If it comes up with short notice, I'll try to get an announcement out on Blackboard right away. But if they give me time, I'll let you know in advance. Okay. Sorry about that. Let's move on. Where we left off last time was in Chapter 7, which is Techniques of Integration. Section 7.6, Strategies for Integration. That's the section not covered in the PowerPoint. So we're just going to do these separately. We started on page 407, and we did number 1, A. But strategy number 1, and not that the number matters, but they just list them this way. Do any algebraic simplification possible. Cancel terms of fractions when possible. And here's a second for instance. We did the first for instance. Here's the second one. If your integration is the integral of x minus x cubed divided by the square root of x dx. Okay? How would you approach that? Say that again. No, yeah, let's not say we did. Okay? Hint algebraic first. See if you can simplify it algebraically.
Well, root x is going to be negative half.
Okay, that is a good first start. This will be the integral. I don't care which one you put first. If you want to put the numerator first, that's fine. X minus x cubed times, how would you? Yeah, x to the negative 1/2 power. Now that's one way to approach it, and that's dx. Okay? Now writing it that way hopefully will help you see, hey, you can distribute that. So let's distribute it. That'd be the integral of, that's x to the minus 1/2 power. That's not very clear, but that's what it is. Times x would be to the 1/2 power. Perfect? Right?
Right. It's a negative. I'm thinking in terms of it's x to the first, and x to the negative half, and my brain wants to say negative times positive. Negative.
Yeah. You're adding, not, multiplying.
Not multiplying.
Right.
All right, and then
Minus.
Minus is going to be x to the 2, and then
Yeah, which I would write is 5/2 power. Except not 5/5, 5/2. The old brains, mouse says one thing, the hand writes something else. 5/2 power dx. How about that? What can you do with that?
well, I think we can actually integrate that.
Yes, exactly.
So that's going to be x to the, we're going to add 1 power, this will be x to the 3/2
3/2 power times
2 over 3,
2/3 minus
x to the 7/2
7/2 power.
times 2 over 7.
Yep.
Yeah,
Let's see. That's it. And they say it's easily integrated. I think we did easily integrate it. Okay? They didn't carry it all the way. We did. How about this one? All right, to erase.
yeah.
Okay. Just because I don't know how much room this is going to take. I don't think it'll take a huge amount of room. 1 over sine squared x dx. Yeah. though I probably wouldn't have done that, but that's what they do. Cosecant squared x dx. And then what do I do with that? I look it up in a table, okay? Which is probably what I would do with sine, to begin with, sine squared, if it's back there like this. I kind of doubt if it is. Getting these pages to work. Okay, here's the integration. Trigonometric forms. Yep, they do list. Well, I was going to say that, but now I don't see it. Actually, what? Yeah, they do have, if you got your book, in the back of the book, equation 49 is the integral of cosecant to the nth power, which is, where n is 2. That would work. But you could also go up to sine to the nth power, but just put an n of minus 2. And frankly, I found that a little more satisfying to work with than cosecant. But either one of them will work. But since the book said go to cosecant, then let's do that, and let's use the one in the back of the book, which is, well, they just give it to you. But using the back of the book will be a minus 1 over had it and I lost it. There it is, number 41. N minus 1, which the n is 2, so that'd be 1. So that's just going to be a minus 1. Cotangent u, so that's cotangent x in this case. And then they say cosecant to the n minus 2, which is just going to be 1. You know, n minus 2, 2 minus 2 is 0. Cosecant to the 0th is 1. And then they have the other term, which you won't need, plus the integral of cosecant to the n minus 2, which is again 1, and the integral of 1 is 0. So that just disappears, so you have minus cotangent x, which they gave you. Which, frankly, if you remember your derivatives of the trig functions, derivative of cotangent is minus cosecant. So, yeah, minus cosecant squared. So you probably should have known that anyway. Okay? And then you do a plus c, of course. Okay. Kayla? Huh? Jasmine, yeah. Sorry. Been a long weekend. A very long weekend. And by the way, I wanted to ask you, did you get the word on time or did you show up Monday? Yeah. Most of the students in my last class did too. I cannot believe they didn't send the email to students. They only put it on the website. And whereas they say, in their silly thing in the thing, check your website, check your email every day before coming to class. They don't say check the website every day before coming to class. So we didn't know about it until Thursday afternoon. Yeah, and it was, I'm going to gripe about that, believe me. Okay. Right. Well, except UAB worked Monday, even though they were a state institution. But, all right. We're on page 407. This is Chapter 7, Techniques of Integration. 7.6 is Strategies for Integration. And we just finished B and C. We're starting on 1D. And 1D has a hyperbolic sign in it. And the way they do it is exactly how I would do it. Rather than trying to do an integration by parts with hyperbolic sign, write the hyperbolic sign as the function. Since they are going to do it what I consider the best way, I'll show you this one, okay? Usually I just skip the hyperbolics. Here's the integral of e to the x hyperbolic sign of x dx. All right. I need Kayla, right? Huh?
Depending on what day it is,
I couldn't hear you.
Depending on what day it is, yes. Yes.
Yes. Okay. My hearing is so bad. And as I've asked everybody else, did you get the word on Monday in time, or did you come?
Oh, I did. I
Okay.
checked the website.
You did. Okay, good. Thanks. They don't tell students check the website before coming to class. They say check your email, and they didn't send an email, and I'm sorry they didn't.
Because my mama told me that they'll like create a state holiday or whatever. So
Right.
I can go Monday, so I was like, they don't have class. And I checked, and it is kind of lit, so I still
Okay. Glad you had the foresight to do it. Now, again, like I was telling you before, I'm sure someone must use hyperbolic functions. I just don't know who. They teach them, they talk about them. But what a hyperbolic function is really an exponential function. They just give it this name, and I'm not even sure why they call it that. But what hyperbolic sign is, and this is all I would remember in it, is e to the x minus e to the minus x over 2. That's what hyperbolic sign is. So when you have something like this, change it to that. The integral of e to the x times e to the x minus e to the minus x dx, and I would put the 1/2 out front because you don't need it in there. Okay, and then it's pretty simple to do from there. What would be your next step? Distribute. Okay, and what would that give you besides the smiley face? E to the 2x minus it's e to the x times e to the minus x. E to the x times 1 over e to the x. That's e to the minus x, right? That's just 1. Boy, does that get easier. 1/2, and what's the antiderivative of e to the 2x? E to the 2x, I can't write, over 2. You have to unchain rule it, kind of, right? And then what's the antiderivative of 1? Just x, okay? And so this would be 1/4 e to the 2x minus x over 2 plus c. Or you could pull out, leave the 1/2 on the outside, 1/2 e to the 2x over 2 minus x plus c. Lots of ways you could write it. They write it the way I did it first. E to the 2x over 4 minus x over 2 plus c. Fantastic. Okay. So, first, if you can do something algebraically to simplify, make it integrable that way, then you don't have to worry about anything else. Do it. use algebra techniques to simplify if possible. If that doesn't work for you, it says look for a potential substitution. Okay? And remember your integration by, well, just substitution first, and see if that, a simple substitution, and if that doesn't work, then do a, one of the other techniques. So let's move to example 1, and that, I think, is going to illustrate what they're talking about. So we'll erase all that ink and have the integral of x cubed times the square root of 1 plus x squared dx. Now, they did a couple of others first. I probably should have done those, but let's do this one. This is not a super simple one. Okay. Now, the first thing I would do is what? Do anyone have a guess? Yeah, write it in exponential notation. That would be x cubed times 1 plus x squared to the 1/2 power dx. Okay. Now, just a hint. If that had been a 1 plus x cubed times x, x to the 1/2 power, then distributing would be a fine thing to do. However, you can't distribute into a radical, so that doesn't work here. So don't try it. Okay, you just can't do that here. Okay. So what might be a substitution you might choose? That's where would be my first guess. So let's try it. And what do you want to call that? Everybody's favorite? U equal 1 plus x squared. Okay, then what? What's your next step in the substitution? du is equal to 2x dx. Okay? We don't have a 2x dx. We have a x cubed dx. But we do, since that's an x squared left over, so let's write what we have then. That would be the integral of x squared. We'll put the 1/2 out front. We'll go on and do this. Divide by 2, divide by 2. So x dx would be that. So you'd have an x squared, and then you'd have a u to the 1/2 du. Okay. It's stupid to write it that way, but here's the point. The x squared you can't deal with, or can you? Go back to your u up there. Doesn't that have an x squared in it? What does that x squared equal? U minus 1, right? You see what I'm talking about? You can rewrite this as then u plus u minus 1 is equal to x squared. You can put that in here. Okay? So this will be 1/2 the integral of u minus 1 times u to the 1/2 du. Hey, what I just said was if you had a binomial there and a fractional exponent on the outside, you can distribute that. You can't do a fractional if your exponent was a 2 or 3 term exponent. that's a fractional exponent. You can't distribute the other way, but you can distribute this way. So what would this be? 1/2 the integral of distribute. U times u to the 1/2 is u to the 3/2 minus u to the 1/2. You can distribute that way, you can't distribute this way, okay? If you have the radical that has a polynomial in it, you can't distribute there, but if you have a regular polynomial, you can distribute a single term radical into that. So this will be du, and I think we can do that integral, 1/2 what? U to the what? 5/2, okay, times what? 2/5 minus u to the 3/2 times 2/3, and then you're going to have a plus c out here somewhere. I wouldn't worry about it yet. So this would give you, writing somewhere else where we have room, here, the 2 will go into both of those 2's, so you have u to the 5/2 over 5 minus u to the 3/2 over 3 plus c, but guess what? We started with x's, we need to end with x's. So what is u? 1 plus x squared to the 5/2 over 5 minus 1 plus x squared to the 3/2, I lost my place there, over 3 plus c. And there we have it back in terms of what we had to begin with. So sometimes the substitutions aren't super simple, but fiddle around with them some to see if you can find any way to make them work a little better. And that one, since you had an unaccounted for x squared, because your u covered that, your du covered 1x, you had 2 x's left, x squared left. But guess what? Your u had an x squared in it, so rearrange that. So x squared is equal to u minus 1. Plug that in here. Yeah, you got it. Okay. Yeah. Okay, say that one more time. Yeah. Yeah. du is equal to 2x dx from here. I divided the 2 because we didn't have a 2x dx instead of x dx. So this will give me du over 2 is equal to x dx. We'll take one of these x's with dx, that made your du. This became u to the 1/2, and this was an x squared you couldn't do anything with. Until you went up and noticed there, and it's probably not good form to put actually using the same radical, same integral. I'm only doing that for effect here, so you can see you need to get this in terms of u. Well, that allows you to get it in terms of u, because you can subtract 1 here, and that gives you x squared. And that then gave you u minus 1. Not u minus 1 squared, but u minus 1 is x squared, so that's 1. So yeah, that's the little trick that we played here. The du over 2 brought the 1/2 on the outside here, and the rest of it is just algebra, basically. Okay. Let's see what they wound up with as answer. 1 plus x squared to the 5/2 over 5 minus 1 plus x squared to the 3/2 over 3 plus c. Good for them. They got it right. All right. And here's another. It's a bit bizarre looking. The integral of dx over the square root of the square root of x plus 1. Boy, what a messed up looking problem that is. All right, where would you begin? Okay, here's where I would start now. Maybe it'd be okay not to do it here, but I still think a good idea is to get rid of radicals and write it as powers. Okay, so let's try that. I'm not sure this will be particularly helpful here, but let's just see what happens. That would be this thing in parentheses to the 1/2 power, and the thing in parentheses is x to the 1/2 plus 1. Do you agree with that? Okay. Now, where would you go from there? And we can take off and go on a tangent that won't work. I mean, it looks like it might, but we could try it. Where would you go? My general rule for substitution is find the innermost part of the most complicated part of the function. And that I would play to be this. Or maybe the whole thing here. So let's try it this way. Let u equal x to the 1/2 plus 1. Let's just try that and see if it works. What's our next step? Then du is equal to (1/2) u to the minus 1/2, isn't it? Oh, 1/2 x to the minus, I'm sorry. X to the minus 1/2, right? Dx. All right, that doesn't seem very helpful, does it? What's that? Like I said, sometimes you might try something and it may not work, okay? But let's not quite give up on it yet unless we can see something else to do here. In fact, I don't see anything particularly we can do with that. Can you? What's that again? Okay. My other guess, before I do, is what if we had u equal just x to the 1/2? Then du would be 1/2 x to the minus 1/2, just the same as we had here, dx. I'm not sure that's any better or worse. But let's actually, what they did, and this is a trick, I was trying to remember it. They started exactly like we did, okay? Except that before you take your du, let's rearrange some stuff, okay? And write this as sort of like we did before, then x to the 1/2 is equal to u minus 1. Okay? Now, du would then be negative 1/2 x to the minus 1/2. Okay? What's that? Which would be negative 1/2 times x to the 1/2. The x to the 1/2 is u minus 1. So that would be dx here. Dx here. And this would be a negative 1/2 times u minus 1 dx. So minus 2 u minus 1 du is equal to dx. Okay. I think that may give us what we want. Okay. Now, again, it's a trick sort of like before. Your first inclination was let the innermost part, your most complicated part, be that. Okay. Now, there's a couple ways you can do it now. See, there's an easier way to get to where we were getting. If you did this and then say, then let x to, then that would mean x to the 1/2 is u minus 1. Same as we did before. Now, I'm going to back off a minute here and do it yet another way. Take the derivative of this, and that would be 1/2 x to the minus 1/2. I'm not sure that's any easier. Dx is equal to du. That would still give us the same thing we have here. But what you do now is get the solve for dx. So all you have is a dx here, and that would be this du. So you put this in for the du here, and then you put the rest of it in here. And let's just see what that gives us. Okay. It'll be the integral. Your dx is a minus 2. I'm going to put that out front. U minus 1 du. That's from here. Over, and this would be u to the 1/2, because that's where we started with. U to the 1/2. Okay? Which I would then write this as the integral of u, of minus 2 out front, u to the minus 1/2 times u minus 1 du. And sure enough, that's something just like we did before, minus 2 integral of, and do that. Distribute that. What would you have? I'm sorry? This right here. You have this, yeah. So distribute that both ways here. What would that give you? Second? Use to the positive 1/2. minus u to the minus 1/2 du. Okay? And this will be minus 2 times, and what does that give you? No? Add 1. Your antiderivative. 2/3 minus, yes, times 2. Okay? You'll have a plus c out here after a while, but this gives you minus 4/3 u to the 3/2 plus 4 u to the 1/2 plus c. And now you go back and plug in what your u is. Minus 4/3 x to the 1/2 plus 1 to the 3/2 power plus 4 x to the 1/2 plus 1 to the 1/2 power plus c. I think that's about as simple as you can write it. If they want you to go back and put it in radical form, yuck, that would be a minus 4/3 the square root of x plus 1 cubed plus 4 times the square root of x plus 1 plus c. I don't know if they want you to go do that or not. Let's see. No, they left it in exponential form, which is, and now here's the other thing. They sort of hate they did this, but I mean it's perfectly fine. They multiplied everything by minus 1. They did the problem a little differently. Got 4/3. Well, they wrote some of it in They wrote some of it in radical form and some of it in exponential form. 4/3 the square root of x plus 1 to the 3/2 minus 4. They multiplied everything by minus 1. Square root of x plus 1 to the 1/2 plus c. Let me make sure. I think that's fine. Seems like to me it should be negative plus, and they have plus minus, but let me make sure I didn't make a dumb error somewhere in there. I did make a dumb error somewhere. du would be 1/2, not minus 1/2. So that minus sign should not have been in there anywhere. Okay, so that's a plus and that's a minus. Sorry about that. I don't know where I came up with the minus sign there. I may not have covered them all, but yeah, go back and sorry about that. Okay. Number 3, rule number 3. Number 1, simplify algebraically as much as you can. Example 2, substitute if you can. Number 3, consider integration by parts. If you can't work your way around it, do that. And we've just done integration by parts not too long ago. So let's just do one example of it. I think it's one we've probably already done, but just to remind ourselves what that is. What if we had the integral of x e to the x? Okay. Now, there's no substitution, no algebraic manipulation, nothing else I can think of to handle that. Okay. The key that I look for here is the fact it's a product. Okay. And so I think not integration, but differentiation, sort of the product rule, and integration by parts came from the product rule. You remember how that went? Almost looks like a substitution to begin with. What you do, you take part of that and make it your u, and another part and make it your dv. Okay? Now, what you're going to do to the u is differentiate it. So you want a part that gets simpler when you differentiate. And when you start with the dv, you're going to integrate the dv to get a part, to get a v, and you want to use that part to be one that doesn't get any worse. Okay? So your integration, your differentiation should make it better. Your integration just shouldn't make it any worse. So when you choose your parts, which part would you choose to be what? Which would be the u, which would be the dv? Say that again? Yeah, you let u equal x and dv, e to the x dx. Always have the dx with the dv, by the way, okay? Then, and what you have to do is, like I just said, on the u part, take du is equal to 1 dx. Right, we're doing it in differential form. And what would your v be then? E to the x. And don't worry about your plus c's. We'll do that at the end. Okay? Now, integration by parts tells us you start with the u and the v, so this would be equal to the product of those two, which would be x e to the x minus the bottom line here, what you have left over. And that would be e to the x dx, which to me is something real simple to integrate. What would that give you? X e to the x from the uv part. And what's the integral of e to the x dx? E to the x. And there's where you put your plus c then. Okay? All right. Now, here's, sorry, my throat is clogging up on me. Having trouble talking. Here are a couple of hints they give. If your integral, when you're considering integration by parts, integral x to the n f of x dx. Okay? In general, this will be your u, that will be your dv. Here's when it will work, here's when it won't. If the n is 1 or greater, go for it. That's it. As long as the f of x doesn't get more complicated when you integrate it. In other words, if it's an exponential function or a sine or a cosine function, then when you integrate that, you wind up with an exponential or you wind up with a sine or a cosine. So it doesn't get any worse. Okay? But do not do it this way if n is a negative number to begin with. It's just going to get worse. Okay? So this is good if n is 1 or greater, and if alpha of x doesn't get any worse when you integrate it. Okay? Now, the B example here is this one. The integration of e to the x sine x dx. When you have that kind of a problem, that's really a great kind of problem, okay? You can use either one of them to be the x and u, and either one of them to be the dv, okay? I kind of prefer to let the sine be the x and the e to the x dx be dv, because I know every time I integrate that, it's just going to be e to the x, okay? When you differentiate sines, you could have integrated the sines, but it's a lot easier to make a SIG and sign error there than if you did it the other way. When you're differentiating, to me, I know those signs, and I tend not to make the errors as much. But you can do it either way. That one will work either way. It's going to be a two-step problem, because after a while, you're going to get back to the same form you had before, and then you can solve it that way. We did one in the book that way. And let's actually do this one, okay? So which way you want to try? Say that a little bit slower and louder. Okay, that's what I said. Okay, u equals sine x, and dv is equal to e to the x dx. Now remember that, because you're going to come back. Then, what do you do next? du is equal to cosine x dx, and v is equal to e to the x. Okay? Remember, we're going to save our constants till the end. What's your next step? Okay, your uv would be sine x e to the x, okay, or e to the x sine x, it doesn't matter, minus what? Yeah, the integral of e to the x cosine x dx. Okay? Now, still can't do that one. But here's the key, folks. Okay? When you do the next step, keep your u's and the dv's similar to what you had before. Now, if you want to change letters so you don't have to remember that, but here it really doesn't matter. Let u equal, and that last time it was a trig function, this time it needs to be a trig function. Cosine x and dv is equal to e to the x dx. Okay? Then du is equal to negative sine x and e to the x. Say that again. Yeah, there's a dx with here. Is that what you're saying? My hearing's so bad. Okay, and what does this part? Now remember, don't forget you had a sine x e to the x, or e to the x sine x. In fact, I think it probably is better the way you said it. Yuck. Because I think it's easier to make a mistake the other way. E to the x sine x, okay, that's out front, minus your uv e to the x cosine x, minus a minus is a plus, integral of, okay, so now that makes it minus again. You have to keep up with all these signs. Okay. You had a minus in front of that integral, right? Then you were doing this. So this was this, which the minus went with that, minus this part, so that's the minus that you have here plus a minus there. And then the third one is that. So you wind up back at a minus again. That's those signs, SIGN signs, are sometimes the trickiest part of these problems. And that would be e to the x sine x dx, right? And all this was the integral of e to the x sine x dx. Now, by doing integration by parts, you just would keep going and going and going like the Energizer Bunny and never get anywhere. Okay? But once you get to this step, you see when you did it first time, you wound up with that, which you can't do. Now you wound up what you started with again. Have you messed up? No. Add this to this side of the equation, you get 2 of these is equal to that, divide by 2. And that's exactly what you do. Add integral e to the x sine x dx to both sides. And that's equal to this thing. Okay? Okay? So you get, or we'll write it up here somewhere, 2 times the integral of e to the x sine x dx is equal to e to the x sine x minus e to the x cosine x, and then divide both sides by 2. And that original integral is now that. You never actually solved the integral, but you had an equation with it on both sides, and then you solved it that way. Okay. And then you put, of course, a plus c out here. Okay. That would be 1/2 minus e to the x cosine x, while they launched out with the minus, I'm not sure, plus e to the x sine x plus c. Got it. Okay. Now, there's one other sort of a strange one that we sort of break a little bit of one of my rules on, and that's this one. What if you had the integral of log x dx? I don't know the antiderivative for log x. I know what the derivative of log x is, but I don't know what its antiderivative is. So this doesn't actually sort of seem like it has a u and a v, except, remember, here's one of the rules, the dv has to have the dx in it. So that would then leave the u to be log x, and the dv to be dx. Okay? Now, where this sort of breaks a rule, when you integrate the dx, it actually gets more complicated. Remember, we said try to have it so it won't. No way around it here. But let's do our derivatives and see what happens. Then, what's the next step? du is equal to 1 over x dx, and then v is equal to x. Goodness gracious. All right. Not even an hour and 10 minutes into the class, and I'm feeling pretty lousy here, but let's truck on and see what we get. What do we get? uv is x log x minus, you see, always that second part, and what goes here? X over x, which is 1 dx. Hey, we can do that, can't we? That would be x log x minus antiderivative of dx second of dx, right, x plus c. And there you have it. Okay. Oh, I thought they were doing this. I'm sorry. I didn't see it. Now, they also mention in the same breath almost as log x, which is a fairly simple one to do, the integral of an inverse tangent x dx and the inverse sine x dx, any of those, you use the same technique. You let your u be the inverse tangent and put your dx to be the dv to be the dx, and that's all that's there. And then when you need to go back and plug in, everything will work out. Okay. My stomach's hurting. I'm just feeling blousy all over the place. And just have the dv be the dx. All right. Now, step number, or question number 4, or thing to look at number 4. Number 1, of course, is see if you can simplify algebraically. Number 2, see if you can substitute. Number 3 was integration by parts. And number 4 is consider the form of the integral. Does it fall into a category for which you have a technique? Number 1 is a trigonometric integral, and that basically look it up in a table. However, a lot of those will use a form of and different texts call them different things. Power reduction formula, which goes from a square of a trig function to either the same or a different trig function to the second, not to the second power, but to double. So you can look over that technique, which basically means, look it up in a table almost, maybe not always, but something like that. The second part is, does the integral contain one of these 3 forms? And these are the ones we did earlier. Now that was a trigonometric integral. This is a trigonometric substitution. A squared minus x squared, the square root of x squared minus a squared, or the square root of x squared plus a squared. All right, and if he has any of those, we'll use our trig substitutions. What trig substitution would we use for this one? The first one, square root of a squared minus x squared. Because, say again? Let x equal a sine theta. Okay? That would be your substitution, because when you do that, you'll have a squared minus a squared sine squared theta, which would then be a that you can pull on the outside of the radical, 1 minus sine squared, which is cosine squared, and that disappears. Okay? When you have the second of the forms there, I actually like the third one first. Let's go for it. And that, by the way, could be either a squared plus x squared or x squared plus a squared. It doesn't really matter. This substitution would be let x equal a tangent theta. Okay? And the third one then would be let x equal a secant theta. All right. Goodness gracious. All right. So those would be the substitutions I would make. So let's do example 3. I'm going to erase them, so hopefully you sort of got the idea down. Let's do example 3. Evaluate this. The integral of x squared plus 16 to the 3/2 power dx. Start from the beginning. There is no algebraic manipulation you can do to simplify that at all. Substitution, nah. If you try to do let u equal the innermost part, you're going to have a du is equal to 2x dx. That x you can't get rid of. Okay? Nothing there. Integration by parts doesn't qualify. It's not a product of anything. So if you let the first part be your u and the last part be your dv, when you go to integrate or differentiate that, it gets pathetically difficult and just keeps getting more difficult. So don't go there. So this looks like one of your other tricks as far as a trig substitution. Which one of them does this fit the pattern? Second, tangent. Okay, so what would you have? Let x equal 4 tangent theta. Perfect. Okay, then dx is equal to what? That would be 4 secant squared theta, d theta. All right, let's play around with this thing that you've got here. This leads to, you want an x squared is equal to 16 tangent squared theta, right? You're just squaring that, right? Okay. X squared plus 16 then would be 16 tangent squared theta plus 16, which would then be 6. Okay, 16 times tangent squared theta plus 1, that would be 16 times, what's tangent squared theta plus 1? Anyone remember? Pythagorean identity. What would it be? A little louder. Secant squared. Secant squared theta. Okay? So, and then that whole thing to the 3/2 power, you would do the square root of this thing okay? And that would be square root of 16 is 4. Square root of secant squared would be secant theta, and then you cube that, and you have 64, I'm not sure you need this, 64 secant cubed theta. Okay. Lots of maneuvering there. Let's rewrite our integral now. It's the integral of the x squared plus 16 was your 4 secant theta, okay, and that to the 3/2 power would be 64, 64 secant cubed theta, and your dx was another 4, so let's pull these on the outside here. 4 times 64 is 256 secant 5th theta. You had secant sort of gotten lost here a minute. D theta, okay, there it is. I knew it was somewhere here. There's your dx there. So you had 64, so 256, okay. Now, secant 5th, again, I would go to a table. If you've got it memorized, then go for it. If you know the procedure, go for it. But it's just as easy to go to the table, and you're doing secant 5th, which would be number 48 in the back, the integral of secant to the nth. Okay, so we've got a 256 secant 5th theta d theta. That would be 1 over 4, n minus 1, that would be 4, tangent theta secant n minus 2, 5 minus 2 is cubed theta, okay, plus n minus 2, that's 5 minus 2 is 3, over n minus 1, 4. I'm sorry, no, I got it right. Times the integral of secant cubed, n minus 2, theta d theta. Okay. Now if you go back to number 42, you see what secant cubed is. So this will be a 256 times 1/4 tangent theta secant cubed theta, plus 3/4. And now we do another bracket now. This will be 1/2 secant theta tangent theta plus 1/2 log absolute value secant theta plus tangent theta. Okay, and then you'll have a plus c. All right, now, whenever you're doing these, the trig substitutions, always, 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 always draw your triangles, okay? From that very first substitution you had here, where x is equal to 4 tangent theta, rewrite that as x over 4 is equal to tangent theta, okay? And that gives you your triangle. If this is your angle theta, tangent theta is opposite over adjacent, so this will be x, this will be 4. Okay? That puts this to be the square root of x squared plus 16, which is square root of x squared plus 16, and that would be, from what we did before, that basically is your thing right here, okay? That's going to give you just about everything you need, just having this. So let's go back to our last solution, which I hope I didn't do anything dumb here, so I'm going to erase here and use the line below it. And our trig substitution, okay? All right. Now let's start with this. Let's do these fourths into 256, and that'll be 64. Okay, so you don't have to worry about that anymore. So it'll be 64 times tangent theta we know already to be x over 4, and secant theta to be, secant theta is hypotenuse over adjacent, so that would be times the square root of x squared plus 16 over 4, okay? But you're cubing this, so that would be I'm just going to write it cubed that way. It's easier that way. Plus 3 times 1/2 secant theta would be the square root of x squared plus 16 over 4 times tangent theta was x over 4. Okay. Plus 1/2 the log I don't know if we need this or not. I'm going to keep them just in case. The square root of x squared plus 16 over 4 plus 1 over 4. I mean x over 4. Okay. Plus c. Now, the reason I said I wasn't sure if we need this anymore, we know this is always a positive number. Always. And this x could be negative. If that x is negative, when you add it to this, since they have the same denominator, when you add it to this thing is always positive. Because this thing's always a great deal more than x. Because the square root of x squared would be x, but you got x squared of x squared plus 16, which would be greater than x. So I think you could lose your absolute value bars there. Okay. Now, is there anything else you can lose? This is a 4 times 4, which is 16, so this could be just 4 here. So let's see if that helps any. 4 times x square root of x squared plus 16 cubed. Oh wait, messed that up. 4 times, oh wait, this 64 goes into this, so this is 1/4. 1/4, okay. Plus, and here we have 4 times 4 is 16, times 2 is 32, so that would leave 2, so this would be a 6 here. X times the square root of x squared plus 16 plus 1/2 of 64 is 32 times the log of the square root of x squared plus 16 plus x over 4 plus c. I think that's the simplest way to do the answer. I don't know if that's what they got in the book. Really a big pain in the neck. Oh man, I messed up this part. I did. I have 16. I have 1/4. X times that thing to the 3/2 power plus 24. X times that to the 1/2 power plus 96. And they kept the absolute values in there. Plus c. Looks like I probably did make a dumb math error somewhere, but rather than trying to chase it down, follow it in the book, you'll probably find the math error I made. It has to do with the thing out front, that 256. I may have canceled too much out too quickly. I don't know. Now, number 4, consider the form. Also under considering the form, let me clear this one out of the way, is this one. When you see any integral that looks like this, the integral of x squared plus 2x plus 10 over x squared plus x minus 6 dx. Now, what comes to mind when you look at an integral like that? Okay, now I think you hit something there. When I see that, first thing comes to my mind, factor everything in sight. It may or may not be beneficial, but try it to begin with. Again, that's going back to algebraic, simplification. So that numerator, will it factor? Okay, how will it factor? Yeah. No, it won't. Will it? Huh? Yeah, I think that's a 10. I can't read my writing. It will not factor. Okay? I thought x plus 5 times x plus 2, that would be x squared plus 7x plus 10. No, it will not factor. Good try. And that's what I would do first, though, is see if you can factor it, because you want to eliminate any common factors, okay? But there aren't any, because that numerator will not factor, okay? Say that again now. Okay. Let's... I want to mention this now. The denominator will factor, by the way. Okay, how will it factor? Absolutely. Okay, so there you have a factorable denominator into linear factors. What should pop into your mind now, especially since that numerator is not factorable, this looks like a problem for partial fractions. However, does that form fit the rule for partial fractions? If not, what's wrong with it? What has to be true about your partial fractions before you can do it? The degree of the numerator must be less than the degree of the denominator. They're the same. So since they're the same, or if the numerator was actually a greater degree, what would you do first? I know it's sort of a pain in the neck, but you got to do it. Long division. Division of the polynomial. So let's take it and divide it. It would be x squared plus x minus 6 divided into x squared plus 2x plus 10. Now, requirements for long division, you have to account for every term. We've done so. Start from the outside, left to right. Only operation we do this way. X squared to x squared will go one time. Multiply x squared plus x minus 6. And then normally we subtract with long division. I change signs and add. Make that a minus, that a plus, and the middle one a minus. Okay? And now add. Well, these add to 0, which is exactly what we want. And that leaves us x plus 16. Okay? So I rewrite this integral as the integral of dx, that's the 1, plus the integral of x plus 16 dx, that's a remainder, over our denominator. But now, let's, as you said, factor that denominator. How does it factor? Right. Okay. That part we want to do partial fractions. This I can do. X. Okay. Antiderivative of that is x. Okay. Now we got the partial fractions to deal with. Let's go off to the side and do that. What we want is x plus 16 over x plus 3 times x minus 2 equals sum a over x plus 3 plus b over x minus 2. What do we do to solve that? Multiply both sides by your denominator. Okay? That will be that, and this left with x minus 2. And when you multiply this by that, that wipes out, and multiply that by x plus 3. Okay. So I'm going to do this a little bit. X plus 16 is equal to a times x minus 2 plus b times x minus 3. No, plus 3. Sorry. Okay? Now what do we do? Okay, first we'll say let x equal positive 2. Then what does the left-hand side become? 18 is equal to, and that will go away, and this will be b times 5. Oh, boo hiss, what a ugly fraction. Let me make sure I haven't made a dumb mistake. Nope, I think we got it. So what's your b? b is equal to 18/5. Nothing much we can do about that. But then, what's your second let? X equal -3. Then what's the left-hand side become? 13 is equal to a times -5. And that implies that a is equal to okay. Now we'll go back and plug in here. This will be, just to keep things right here, make that a minus for the first part, minus 13/5, that's your a, and the integral of dx over x plus 3 plus 18/5 times the integral of dx over x minus 2. I think we can do that one fairly easily. X, don't forget the x, minus 13/5, that integral. Second, natural log of x plus 3. We'll put that as absolute value, plus 18/5 times the natural log of x minus 2. Oh, plus c. Yuck. Okay. I know it's a little messy. In fact, it's very messy. Let me clean that up just a little bit here. Yep, too much. Okay. All right, that is what I found the answer to be. Let's see what they got. X minus 13/15 absolute log of absolute value x plus 3 plus 8/5 log of absolute value x minus 2 plus c. Okay. And then, even though we've already been doing it, they say use the integration table, and they give you a few examples of it as well. So let's do one. Evaluate the integral of the square root of 9 minus 4x squared over x dx. Now, first glance, you might think a trig substitution, where x is equal to, say again? I can't hear. Yeah, well, that's what, okay. Just a regular substitution. If that x had been in the numerator, perfect, but it's in the denominator. So then the next thing you might think of is a trig substitution, but how do you get rid of the x then too? That's a problem there as well. Then you may think integration by parts, but I think that would turn out being really, really messy, because nothing gets any simpler as you keep taking either derivatives or integrals. So I think we have to just go straight to the table. Now, except I don't think you're going to find that form in the table per se. I'm not sure. I'll go look in a minute. But I think I would rewrite this as the integral of 9 over x squared minus 4. Now, I'm not sure that's going to be helpful, but I think that's the same form because it's the I don't think that's going to be helpful at all, but I thought it might. But let's go back to the table and see what we can find. And under table of integrals, it's definitely not a basic form, not with the radical being on the top rather than the bottom. It's not exponential or logarithmic forms, hang that up. Hyperbolic, hang that up, period. Trigonometric, not. Inverse trig, nope. Fact, forms involving the square root of a squared minus u squared. That's beginning to look like that, at least the first one there, okay? And if you look at number 69 in the back, that is really looking fairly close, okay? It's this form here, the integral of square root of a squared minus u squared over u du. Okay? Now the u is fine everywhere else except in that numerator. And what I would do to the numerator is this. Rewrite this as the square root of 9 over 4 plus x squared with a 2 on the outside. Okay, let's see if that works. I'm just talking about doing an algebraic change to the numerator. Well, 2, of course, 2 squared is 4. So that would be the square root of 4 if it was on the inside. 4 times this would be 9. 4 times that would be, whoops, that's a minus, so I'll put a plus. Yuck. Is that going to mess me up? No, I just wrote it wrong. It has to be a minus. Okay. So I think that's going to be pretty much what we want. Okay. So basically, what this will be, so forget about my first effort there. I thought that might help, but it didn't. Okay. So this is going to be 2 times the integral of the square root of 9/4 minus x squared over x dx. Okay? Now, in this case, the a is 2/3. I mean 3/2. A is 3/2. So using the table here, we get a 2 times the, probably shouldn't write the integral again. 2 times, and the integral of that, number 69, is the square root of 9/4 minus x squared minus 3/2, that's your a, the log of absolute value, your a is 3/2, plus the square root of your a squared minus u squared, which is 9/4 minus x squared, over your u, which is x in this case, plus c. Okay. Now, when you multiply that 2 times the first, you go back to exactly what you started with, the square root of 9 minus 4x squared, minus 3 times the log of absolute value 3/2 plus the square root of 9/4 minus x squared all over x plus c. Now that's what I got. Let's see what they got. Goodness, I've lost where we were. Oh, there we are. Example 5. Square root of 9 minus x squared minus 3 times the log of, now they pulled the 2 down into the denominator, which is perfectly fine. They multiplied the numerator by 2 and the denominator by 2. So this would be the square root of 9 minus 4x squared minus 3 times the log of absolute value. And this 2 cancels that out. 3 plus, and when you multiply this by 2, you wind up getting exactly that same radical you had, 9 minus 4x squared over 2x now plus c. So, yeah. Again, there's sometimes it seems like dozens of ways you can write the answer. There's not that many, but there are a lot, and I'm just trying to rationalize and see that we got the same thing. Okay. I'm okay. Are any of you, either of you, needing a break? You got to leave at 1, so let's keep trucking, and then when you leave, I'll ask Peyton if he needs a break, but we'll see. All right, let's do example 6. The integral of x sine squared x cosine x dx. Okay. And by the way, they did say that previous one could have been a trig substitution. I thought it could be, but it looked like it, but then you'd have another substitution on top of it. So rather than do that, just do the table. Okay. This, what in the world are we going to do with this?
It's very close to being trig identity, but it's not.
Say that again. Okay, now that certainly would be a possibility.
Yeah.
Okay. Use the sine squared identity to make it into cosine, and you have everything in terms of cosine. And then it still looks like you're going to need an integration by parts.
Yeah,
It looks like it's going to have to be there, but sometimes they get messy, especially in that you got to do one and then the other, and when I look at the right-hand side, rather than doing the trig substitution you're talking about, notice here, just forget this, if that was your problem, that u equals sine x, then du would be cosine x dx, and this would be u squared du, right? And then if x is in there, so if we have this be our dv and this be our u, I think that might work. Let's try it and see. Okay. Let u equal x, dv is equal to sine squared x cosine x dx. Right? Then du is equal to dx, and v would be equal to, you integrated that, you would have sine cubed over 3. Sine cubed x over 3. I think. Let's take a derivative and see. This 3 times 1/3 would be 1. Sine squared x times cosine x dx. I believe that's right. Do you agree? Now, we may have just exchanged one problem for another, but at least you got rid of the x here, okay? So this would then be the product of those two, which is x sine cubed x over 3 minus the integral of 1/3, I'm going to put the 1/3 on the outside, sine cubed x dx. Okay. Again, I go back to the back to see if that's a trigonometric form. Sine cubed u, yep, there it is. So this would be an x sine cubed x over 3 minus 1/3, and sine cubed u du would be another minus 1/3, so that makes it a plus 1/9 times 2 plus sine squared x times cosine x plus c. Okay, let's see if that's what they get. 1/3 x sine cubed x plus 1/9 2 times sine squared x cosine x plus c. Now, that took a couple of things. Number one, realizing there's no way to mess with the x's and sines and cosines unless you do it by parts. And recognizing this part here is a perfect derivative. If you recognize that and then do your u over here, yeah, things work out pretty nicely. You still have to use the table for that second part, unless you happen to remember what that rule is for sine. And you would use, you could say that as a sine times a 1 minus sine squared, and sine squared is 1 minus cosine squared, and you could go through it and do the trigonometric integral that way. The table is just a lot quicker. Okay. Now this one almost smells like that, but be careful. Here's example 7. The integral of x times the square root of x squared minus 4x minus 5 dx. Okay. Now, what's that? If I have your work, I can give partial credit. If I don't have work, I just have to mark them. Huh? What's that?
You can't follow it.
Well, that's up to you.
I don't work to use like.
Yeah. Okay. All right. Now you know you left that in blank, right?
Oh, that's 2 blank.
2 blanks. Okay.
That's what you use like contact and everything else. I couldn't get anything that seemed reasonable.
Okay.
Yeah, I have an issue with doing my work. So scatterbrained to do pieces of problems all over the place.
Right.
It was difficult when you get to be coherent to do, especially because I realized 2 questions on, oh crap, this rule actually applied to a previous problem, and I had to go back and redo the whole part of the problem. I'd forgotten at one point to multiply the volumes by pi.
Right.
When they were both solids. I was like, oh no.
Yeah.
I'm going to go find this in terms of
Right.
pi.
Yeah, you'll see I'm pretty scattered too, but you got to have some form to it, or otherwise you just.
Yeah, that's why like the 2 I left blank. That was after you was working on like so many times, and after that I was just like, you know what?
Yeah. But you see, if you turn in the work when you do something like that, if I find any thread that's making sense, I can give you some partial credit for it.
Like I said, the next test I got you on that, but this test I was just like.
Okay.
I tried
All right.
all my integrals I eventually arrived at on the paper before I started to integrate.
Right. Yeah. All right. Where do you want to head on this one? Do you need a little break before we get going, or?
Oh, no, we can try to do this one.
Okay.
So should we put this in terms of the whole radical being the 1/2? Or
What's that?
Would it be better to put this in terms of the radicals, all the things in it?
Yeah.
1/2?
That's never a bad idea, I don't think. Integral of x times x squared minus 4x minus 5 to the 1/2 power dx. Okay. Okay. Make sure I got my signs right. Okay, now. There are a couple of ways perhaps to head on this one. Number 1, the derivative of the inside is 2x minus 4. You have an x on the outside, but you don't have a minus 4. So that's a little bit of a problem. So I wouldn't say a substitution straightforward will do it for you. The other thing you might try, and I think this offers the better possibilities, is to, I know it's sort of a pain in the neck, complete the square of the thing on the inside of the radical. Okay? And you remember how to complete the square? X squared minus 4x minus 5. That's the same thing we had before. I just left a gap there, right?
Yeah. So it's going to be x.
Take half of the 4. Yeah. Take half of 4, and that gives you 2. Square that, and you get a plus 4. You just added 4, so now you have to subtract 4. Okay? So this gives you x minus 2 squared, right? Perfect square, minus 9.
Oh, I see. Okay.
Oh, you have it?
No. When I was completing the square, it's always been with things that go perfectly into the square, and it's never.
Yeah. But you agree we got it the same? Yeah. Okay. So let's see what happens if we rewrite that. Integral of x times x minus 2 squared minus 9 to the 1/2 dx. Say that again.
Would it be the case
Oh,
that
no, oh, wait. You mean take a square root of that and square root of that? Is that,
Yes.
please not say that.
well,
Yeah. No. You can't distribute an exponent around, you know that. That doesn't work. Okay, but what this does give you is a form that derivative of this, let's let what's in here be your u, and then the du is dx. No, okay. Let me rephrase this. Let that be your u, I think. Okay? X minus 2 squared is your u. Then du would be 2 times x minus 2. It still doesn't work. dx. That doesn't work because, but now you have in a form that is a trig substitution. Okay? And that trig substitution now will be a secant.
is there any way that I can remember to easily identify if it's going to be a secant or is it just
Here's what I use. I don't know if this is helpful to you or not. Think back to your good old Pythagorean identities. Okay? Sine squared theta plus cosine squared theta is equal to 1. And then do sine squared theta is equal to 1 minus cosine squared theta, right? And think of this as, say, b squared is equal to 1 minus a squared. Okay? So if you do a square root of this, you get b is equal to the square root of 1 minus a squared. Okay? Yeah. So that then tells me do a sign substitution. Okay? Let go. And if this turns out being a number in front, then deal with that too. So that form is going to be a sign. Okay? And that basically generalizes to a squared minus x squared. Okay? That form is going to be a sign. Okay? Now, let's do another one of the good old Pythagorean identities. In fact, we'll use this one almost twice. Certainly, if you divided everything here by cosine squared, right, this would give you tangent squared theta plus 1 is equal to secant squared theta. Okay? So if you have a form that's the square root of x squared plus 1, a squared, then that's going to be a tangent substitution. Okay? A tangent theta. Okay? But let's just change this ever so slightly to be tangent squared theta is equal to secant squared theta minus 1. That's what we've got here. That's going to be x is equal to a secant theta. Okay, so that's the one I'm going to use here. I'm going to erase it. Now that's what I used to remember. It's kind of a backward way of remembering, but to me it helps. Okay, it's just remembering the form of those trigs of Pythagorean identities. Okay, so what you have here is then the substitution I would make here is let x minus 2 equal 3 times secant theta. Okay. Then dx is equal to 3 secant theta tangent theta, d theta. Okay? And while we're at it, x is equal to 2 plus 3 secant theta, right? Because if you let this be your, like, x squared is now x minus 2 squared, so that's going to be your 3 secant theta over that form. Then this, you can also readjust that and have x is equal to 2 plus 3 secant theta, which we're going to need later, but not necessarily right now. The dx is going to be 3 secant theta tangent theta d theta. Okay? All right. Now let's do our integral. See what we get. The integral of x is 2 plus 3 secant theta times, okay, we got some more things to do here, unfortunately. Using this one here, let's square that, and we have x minus 2 squared is equal to secant squared theta, okay. When you subtract 9 from that, then you have x minus 2 squared minus 9 is equal to 3 times tangent theta, because it's no, I'm sorry, I skipped a step. Shouldn't do that. Okay. That is equal to exactly what I've got there. 9 times secant squared theta minus 1, which is 9 times tangent squared theta. Okay. Then take a square root of this and the square root of that, and you have your argument here, which is 3 tangent theta. So this thing right here is 3 tangent theta. And then your dx is another 3 secant theta tangent theta. And then you have a d theta. Oh man, what have we gotten ourselves into here? Okay. You might want to just look this one up in the back and see what you get. But let's see. The integral of, when you multiply 2 by all this stuff, that's 2 times 9 tangent squared theta secant theta. 2. So let's just make it 18. Tangent squared theta secant theta plus 27 secant theta, secant squared theta, tangent squared theta. Secant squared theta, tangent squared theta, d theta. All right, what a mess. Well, that's two different integrals. and I think I would go to the table at this point. I may have messed it up so badly we can't even find it in the table, but let's see if we can. I'm afraid I have. So let's step back a moment and go back to the forms of square root of u squared minus a squared. Man, I don't see it there either. It would be great if there was a u squared in front, but there's not. It's just a u. So man. I was so close. Everything we've done is right so far, except that you don't need the trig at all. Okay. Yeah. Yeah. I thought I looked and evaluated it. I must have done an evaluation in my head wrong, because I thought that's not going to get us anywhere, but that's exactly where it gets us. So let's start over here. Everything up to that point was okay. In fact, something very similar to what we did later is also okay. Okay. Like they said, let's let u equal x minus 2. What I try to do too much in one step, and that's where it messed up. You need two substitutions here. Then du is equal to dx. Okay? So what we have here then is, and by the way, x is equal to u plus 2. Okay. So what we have here is the integral of u plus 2 times u squared minus 9 to the 1/2 du. Which you can break into two integrals. The first being integral of u times u squared minus 9 to the 1/2 du plus 2 times the integral of u squared minus 9 to the 1/2 du. Okay. That was the key. Keep it simple, stupid. I mean, okay. This one you can do a simple substitution. They use W. W equal U squared minus 9. dW is equal to 2U du, and divide by 2. That's a W. That's why I don't like using W's, because they look too much like the U's if you get carried away. So this would be, that first one would then be the integral of 1/2 W to the 1/2 power dW. I'm pretty sure that's it. Yeah. And we can do that one. That'd be 1/2 W to the 3/2 times 2/3. So that would be 1/3 W to the 3/2. But W is this, so that'd be 1/3 U squared minus 9 to the 3/2. But then U is or x minus 2, so that would be 1/3 x minus 2 squared minus 9 to the 3/2 power. Okay. That's the first integral. The second integral then is going to do the trig substitution, the one we just did. And if you don't want to redo that, you can just look in the back of the book, and that's square root of U squared minus, and that's exactly this one here. And this would be 2 times U over 2 times the square root of U squared minus 9, okay, minus 9 over 2, the log of absolute value U plus square root of U squared plus 9 plus C. Okay. Now, yuck. So your overall answer is, this integral will be 1/3 x minus 2 squared minus 9 to the 3/2 power plus 2, U is x minus 2, so let's just make that x minus 2, times, and U squared would be your x minus x plus 2, x minus 2 squared minus 9 to the 1/2 power minus 9/2, the log of absolute value x minus 2 plus the square root of x minus 2 squared plus 9 to the 1/2 power plus c. Now that's one form. There is another way to write it. Let's see what they used before. Yeah. Because this thing is exactly that thing. Everywhere you see that, plug back in the other one. So this is hazardous because I might make some really dumb mistakes here leading up to this. I'm afraid I just did, but we'll see. Okay, so this is 1/3, and instead of that we're going to put x squared. Well, let's go back and do our radical. Do they do radicals? Yeah, they do. So the square root of x squared minus 4x minus 5 they mix them up. Sorry about this. That first one they write as the 3/2 power because it's so much easier to write that way. Do the 3/2 power plus x minus 2 times the square root of, I don't need that, x squared minus 4x minus 5 minus 9/2, the log of absolute value x minus 2 plus the square root of x squared minus 4x minus 5 plus c. Okay, let's see if that's how they wrote their answer. 1/3 times that to the 3/2 plus x minus 2 times the square root of that minus 9. They dropped a half somewhere here. X minus 2 times that. Okay, I probably already erased the place that oh, when you multiply by 2, you lose the 2 here too, so they got it right. Okay, so yeah, came up with the same answer. Then they talk about computer algebra system. Okay, if you got access to it, by all means use it, but I don't. Huh?
It's a good service called Wolfram Alpha.
What's that?
You know, Wolfram Alpha, the website, can basically do all the computations you can possibly imagine.
Oh, really? I hadn't heard of that.
Oh my gosh. They have an app that's $3. It even integrates with Siri, and it is wonderful. You can ask it anything. You ask it what the semi-major axis of Jupiter's orbit is, or anything like that. And it would spit it out immediately. You can ask it. I tested it with volume of revolved solids. It has difficulty interpreting it, but it does get right.
Wow.
Yeah. It's an amazing computational engine.
All right. Do you find the preliminary questions useful?
I do.
Okay, let's do those. We may not get them all finished, but I think we might. Let's see. Preliminary questions. For each of the following, state what method applies and how one applies it, but do not evaluate the integral. Okay? Integral of x sine x dx. What method would you use to solve that? By parts. Integration by parts. Let's make sure we're in the right. 7.6. Integration by parts. Okay, and they say, how do you use it? Which would you let be what?
We would take the derivative of x and the integral sign.
Say again?
We would take the derivative of
Yeah, let u equal x and dv equal sine x dx. Okay, yeah, you take the derivative of the x and integrate the sine x. Make sure that's the right page here. Integration by parts with u equal x, dv equals sine x dx. Right. Okay. Number 2. The integral of 1 plus x squared dx. No, that's the square root. The square root of 1 plus.
We could do an upgrade on that, but then we have to use
Trig substitution. So it would be a trig substitution. And which one would you do? No. 1 plus x squared. The plus in there gives it a way to be a tangent.
Oh, okay.
Let x equal, and the a is 1, so tangent theta. Okay. So it's a trig substitution. X equal tangent theta. And they went on and said what dx would be. What would that be? Do you remember that?
Dx would be I can't remember the derivative of tangent right now.
Secant squared theta.
Squared, yeah,
D theta. Okay. All right, number 3. The integral, I can't write, the integral of 1 plus x squared over 1 minus x squared. Technique is,
I'm tempted to say you can do it off correctly because it's so similar, but
is what?
I'm tempted to say that you could simplify it with algebra, but because they look so similar, but
Thing is that 1 plus x squared you can't factor.
yeah, because there's nothing you can do with
Yeah.
correctly.
So this is going to be a partial fraction,
Oh yeah, it will be.
but you got to do something first.
It's improper, isn't it?
It's improper, so what do you do to make it proper?
It's synthetic division.
Yeah, well, not synthetic division, long division.
Or long division.
So long division plus partial fractions. Okay? And all they say is partial fractions, but you have to do long division first because it's improper. Right? Number 4, the integral of cosine squared sine x dx.
We've just done this.
What's that?
We've just done this.
Right.
I'm trying to remember the method. By parts would be kind of messy.
Okay, you might be able to do it by parts, but so much easier if you do just a plain old substitution.
Okay, so just to use something. Oh yeah, because one will be.
Yes, one is a, so what would you be? Let,
It would be one who's sine x
no,
would go to be cosine x.
yeah, let u equal cosine x,
Oh yeah.
and then du is equal to
Negative sine x.
negative sine x dx. So yeah,
Cancels out the sine and then leaves us.
yeah, so that takes care of that part, and you have a u squared
Yeah.
minus u squared, something like that.
Yeah.
Okay, so that is number 4. Substitute u is equal to cosine x, du is equal to minus sine x dx. Very good. Okay, that's number 4. Number 5 is the integral of x log x. dx.
X log X?
Yeah, my writing stinks, but
I want to say by parts would be best.
that is exactly right. Okay, which would you let be what?
We would want to take the derivative of X.
Okay.
We know the integral of we only know
It-
the derivative of L and X.
Right.
We want the derivative of L and X, and we want to integrate the X.
Okay.
We want our U to be L and X and our U to be X.
Let, I think what you said to begin with, let u equal log x,
Yeah, yeah.
and dv is equal to x dx. Now that, they say don't do it, but let's see what happens. Du is equal to
This is going to be 1 over X.
dx, and this will be v is equal to x squared over 2. Okay? Now, when you do this part, that's doable. And when you do this, you'll wind up with 1/2 x dx. You can integrate that. So yeah, that's the way to go on that one. It looks like this is number 5. Integration by parts with u equal log x and dv is equal to x log x dx. Very seldom will you do that, dv equal x dx, but this is one case where you would. Okay? Number 6. Huh?
So usually it's a simpler part, unless you don't know the integral of the other
Right.
one, and then you can't do it.
All right. Number 6 then is the integral of the square root of 1 minus x squared dx.
Okay, that's going to be a trick statement.
Yeah, that's going to be a trig substitution. And what will that?
Minus, is that cosine minus 1?
Yeah, that would be let x equal sine theta. Okay, and see how most of your other substitutions are you let u be something here to simplify this. Here you let your variable here be the substitution,
Yeah.
and that's going to be number 6. Trigonometric substitution, x equals sine x. What will your dx be then?
It would be cosine.
Yeah, cosine x. Yeah, it's a cosine theta d theta. Okay. Why they take it one more step, they do. But anyway, get it. Okay. Number 7. I forgot. Didn't see those getting all tangled up here. The integral of sine cubed x cosine squared x dx.
Well, that's very close to being an identity.
What's that?
That almost looks like an identity straight away.
Not quite an identity.
But by parts would do it, but it would be messy, I think.
Yeah, it would be.
Um,
It's kind
substitution would probably
okay.
do it as well.
This is what they call a trigonometric integral. So I don't know if that is its own thing. It's a trig integral as opposed to a trig substitution. And what you do, if one of these is to an odd power, you pull off that. So that would be the integral of sine squared x cosine squared x sine x dx. Okay? Change this one to, you might have been able to do that, but the easier way is change this to 1 minus cosine squared x times cosine squared x times sine x dx, and then multiply that through, and that becomes the integral of cosine squared x minus cosine fourth x times sine x dx. Then split this into 2 integrals, integral of cosine squared x sine x dx, and the other one is minus integral of cosine fourth x sine x dx. And on each of those do a substitution. Let u equal cosine x, then du is sine x dx, or minus sine x dx, right?
Seems like a much
Yeah.
method.
And
Yeah,
then,
I think I looked it up on Khan Academy because I had one in it, and they were talking about doing double angle on that. And that seems a lot simpler than the method.
I think so too. So let's see if the back of the book says double angle. I'm going to shoot them. Trig method, rewrite that, yeah, exactly like we did. Then use the u substitution, u equal cosine x du is minus sine x dx. And then you go from there. Okay, number 8. For each of the following, I'm going to erase all this. How are we doing on time? We are out of time, aren't we? Are we?
We're 140.
Yeah, and that is time. Do you want to continue and do those last 4 next time? Or
It couldn't hurt.
are going? Okay, so we'll start here.
Well, the things I'm going to be here next class.
What's that?
I'm going to be going next class period.
Oh, you will? Okay. That'll be Monday, right?
Yes, sir.
You just don't like coming on Mondays, do you? Okay. All right. So
I didn't
we'll.
expect to miss 2 Mondays.
I didn't either. I hope I won't have to this one, but I might. I'll let you know if that happens. And then we'll move on to 7.7. Now, 7.7, we're just going to do it as a slideshow, okay?
What is that?
It's improper integrals,
Oh,
and we'll just do that, so if you ever need them, you got. And 7.8 is probability in integration, which I think is also pretty much going to be a slideshow. But 7.9 we will do, which is numerical integration. So I'm going to try to have your test ready for you next time.
next Monday or Wednesday?
Probably have it ready Monday. We may not get it far enough for it, but you'll be able to pick it up. All right, good deal.
Sorry, it's such a lonely class.
What's that?